Normally I have a little bit of reticence sort of going over what's precisely given to you in the book, but today that's going to serve a very different purpose, and that's because from the get-go I'll let you know that the commands that are currently in the book don't actually work in the version of STATA that I'm using and the version of STATA that you're using. The command has been modified a little bit, and so I'm going to show you the command that does work, and it will replicate exactly what the book is asking you to do. And it's only a small modification, but it's something important to note at the beginning, so you're going to want to pay some attention to it. So I'm going to follow through along again with the book, and then when we get to the point where the command is new and different, I'll go ahead and let you know. So today is the first day that we're really going to be actually testing whether two quantities differ in some statistical sense. And the way we're going to do that is through proportional testing and also sample means testing. Both of these are sort of walking us to the idea that you can actually quantitatively test something besides simply doing the eyeball test, which is what we've been doing thus far. So I'm going to walk you through some steps that we already know. First off, let's go ahead and get in the right data set. We're going to start with the NES today. And I'm going to show you immediately a new command, and that's going to be the mean command. We're going to take a look at egalitarianism. And I want you to also note that this week, if we're working with the NES or the GSS, instead of typing analytic weight, you're going to want to type in probability weight, or PW. And the reason for that is we're going to be assessing this data as compared to another sample. And I'll explain the intuition behind that in a moment. So probability weight, it's the same weight, but you have to make sure you type it in. So we're going to take a look at the mean of egalitarianism, and it's 10.4, standard error is 0.068, and it gives us the 95% confidence interval. Now, let's talk a little bit about what this 95% confidence interval means. What this 95% confidence interval means is that if we were to retake this sample under very similar conditions to which the NES was initially drawn, that we would be 95% confident that our mean of egalitarianism would fall within this interval. So if we were to take 100 different samples, 95 of those samples would have a mean that would fall within the interval that we have, and 5 of the samples that the mean would fall outside of that interval. We use this, and we use the logic behind this to actually do all of the tests that we're going to do today, which we're going to do tests with the t-test, and we're going to do tests with the z-score. So I want to show you how we get this 95% confidence interval. So the first step that you need to know is when you type DI into STATA, you're basically using STATA as a calculator. So we're going to take the actual mean. Why am I putting an extra decimal point? We're going to take the actual mean and subtract it from 1.96. Now remember, I've been talking about 1.96 forever. 1.96 is the level by which we know when a t-test goes above or below that something is statistically significant. So we're going to multiply that in this case by our standard error, which is 0.0686345. And you're going to see that we come up with, rounded, the bottom of the confidence interval. To get the top of the confidence interval, we're simply going to add it, and you see how we create that confidence interval. So it uses the standard error and 1.96, so and this t-score, to actually assess the range in which we're fairly certain that this mean exists within the population. So that's why we're using the probability weights this time as well, is because we're making assumptions towards the population, whether this data point exists within the population, and we're 95% sure that it falls within this range. So when we're actually going to test against this, there are a couple commands that we can use. So the first command that we need to get used to is lincom. So let's say someone out there in the world says that egalitarianism is, it's actually 12. So when we do lincom minus 12, what we're going to do is that we're going to test the null hypothesis that egalitarianism is equal to 12 in the population. And by getting a significant test, in this case, we essentially know that if we were to get on a sample an egalitarianism score at 12, we would know that we're lying outside of that 95% confidence interval range, that it's one of those 5% or 5 samples that lie outside of the confidence range that we have. So we would probably reject that as actually being the actual population parameter in which we want to obsess. So now how do we actually get this t-score? Well, the same way that we did up here. So let's take our actual mean, 10.46. And subtract 12 from it. So we're going to look at the difference between these two, and then we're going to divide that difference by the standard error. And you're going to see that we get, again, rounded up, 22.3. And so this t-score, we're looking for a t-score above 1.96. To get a t-score that is this high tells us that we're very far outside of that 95% confidence range. We're closer to above 99% in this regard. So we know that that's simply not the case. So let's say if we want to examine differences between groups on this same score. So we're going to take a look at the mean of egalitarianism, but we're going to look at it over gender. You can see this sort of spits out what the mean score is for both of these. You can notice that the mean difference is about 0.7. Now, here is the difference from the book. The book would say that you use lincom egalitarianism male and lincom minus lincom egalitarianism female. That doesn't work. We have to use a different step. So this command, what you need to do is coefficient legend. This is the command that it'll bring up. And you'll have to do it directly after this command. And it'll show you what the legend is for here. Now we want to test whether male is statistically different from female. And the way that we're going to do that is we're going to take this entire coefficient name and subtract it from this entire coefficient name. So what we're doing is we're subtracting male from female. It's exactly what the book tells you to do, but the command is different, and you have to pull this out with the coefficient legend. And the easiest way is simply to copy and paste here. So that's what I was doing. I simply copied and pasted it. And you'll see that we get exactly the same output that the book got. Like this is exactly the same because we did exactly the same thing as the book did, except the command has changed a little bit as they updated versions of the software. So this is the way going forward that you're actually going to have to do your homework and do your analysis. And what you'll see here is that the difference between these two is statistically significant, which shouldn't shock us. Let me show you how you should have known that. So here we have the probability is greater than t, and we have a t-score as 0.0, and the t-score is above 1.96, the absolute value of 1.96. So there are a couple ways in which to identify that this is a statistically significant relationship. First, you look at the probability of greater than it's greater than T. So the general rule of thumb here is we call this a p-score. The general rule of thumb is if the p-score is below 0.05, we call that a statistically significant relationship. 0.05, obviously 95% confidence interval. We're looking at the same idea here. The t-score, if we look at the absolute value, if it's above 1.96, that's another thing that will tell us it's a statistically significant relationship. But let's actually go up and look at the confidence intervals here. The confidence interval for males was 9.8 to 10.2. The female score is 10.8. So it lies outside of the male's 95% confidence interval. And the male score, which is 10.0, lies outside of the female confidence score. So that should have told us from the get-go that this was going to be a statistically significant relationship, that the difference between the two of them was statistically significant. But this is the general form that you're going to have to use to do these assignments. This coefficient legend is going to give you this output, and then you're going to use that output to examine the sample means. So the next example that they give us, that the book does, is this one, in which we examine whether the feeling thermometer score for Trump is different across the race, across three races particularly, and that's over race 3. So the output it's going to give us is now over 3. It's going to give us the breakdown for each of these. So the mean for Hispanic is 29%, mean for black is 22, and the mean for white is 48. Now, it should seem really super intuitive that there is a statistically significant difference between white and black and white and Hispanic. But what we're going to actually look at is to see if there exists a difference between black and Hispanic, a statistically significant difference. Now, before we even estimate this, we can take a look and see that this 95% confidence interval for black ranges from 18.5 to 25.9. And the score for Hispanic is 29. And the confidence interval for Hispanic starts at 25, and the score for black is 22. So there's probably going to be, let me rephrase that, there is absolutely going to be a statistically significant relationship here. But in order to examine it and get us the actual t-score and have it tell us that it's statistically significant, what we're going to have to do is, again, go to this coefficient legend and subtract black from Hispanic. So we're just going to type lincom, copy this one, minus, and we'll just do it again because we know that all we have to change here is 3. So we're subtracting black from Hispanic to see if there's a statistically significant difference between the two. And yes, so we say anything below 0.05, this is below 0.05, and anything higher than 1.96. So yes, there is a statistically significant difference between the feeling thermometer towards Donald Trump in the population between Hispanics and African Americans. No question there. So this is the general rule of thumb. Now things can get a little bit more complicated. So we're going to look at the feeling thermometer towards Trump. But we're going to do it for 2 different variables. We're going to do it for gun ownership, just simple dichotomous variable, yes or no, and we're going to include gender in this regard. So this will give us a display of the mean approval rating for individuals over what will be 4 categories, because we've got 2 dichotomous variables here, so it'll generate 4 categories. Now this output will look a little bit different from what the book has, but it's the same exact output. So this was a male who does not own guns. This is a female who does not own guns. Male who owns guns and a female who owns guns. And we're just simply looking at, the differences in the means. Well, let's say we want to look at difference between females who own guns and females who don't own guns. Let's say that that's something that we want to assess if the mean of these are statistically different. So the only thing we can add is coefficient legend. And we want to subtract that from that. So simply we just do lincom. We take this. If you're wondering what I'm doing, I'm just hitting Control-C so I can copy and paste it. And subtract it from this. And so we're subtracting no gun ownership from gun ownership. We're testing to see if the two are statistically different. That's what this does, is that we know what the mean of them are. Well, let's test, given all the parameters that we have, whether it's statistically different. And what we find is, yes, that they're absolutely statistically different, that individuals, women who don't own guns have a different view of Donald Trump than women who do own guns. And again, had you looked at the 95% confidence intervals around the means, that would have been very obvious up front. But now we have a statistical measure to it. The t-score is 4.41, and the p-value is 0.000. So, yes. So that's the first part of your homework. The second part is doing proportion tests. To do that, we're going to move into the GSS, just to give the example. And the first thing we need to do before we get started is we need to recode a variable, which is actually very easy to do. But since I didn't want to type it out again, I just already copy and pasted the code for right here. So we've generated this variable called domestic spying. And it simply is whether you support or oppose domestic spying. And since we're actually just looking at it, because I want to make sure it did it right, we're just using the analytic weight. And it's not that, it is this. Yeah, so that looks good. So now we're going to do a proportion test. This one's actually very easy, as the command is proportion. In fact, we'll cheat. Yep. And what we can see is here the proportion, it does not look to be all that different, but that's because we haven't added any real controls yet. And so let's say that we want to see whether this is statistically different from 5. So the way in which we do that is again through the lincom command, but first we're going to have to add the coefficient legend again, because we just have to each time. If I can spell legend. All right, perfect. So we're going to examine whether oppose is statistically different from 0.5. So simply just take this, put it down here, and we testing it to a population parameter, we simply can do it. And so what we find out here is that oppose is not statistically different from 0.5, which shouldn't shock us, as our point estimate was very much within the 95% confidence interval. Now let's see if there's any difference in this over race. So the command is again the same. I think that's the one they want me to use. Yep. And as you can see, the output again differs from the book, but it's actually, I think, easier to follow than the way it's displayed in the book. So our interest here is whether examining these to be different. And so the way that we do that is we're actually going to assess the key differences by their z-scores. And we're actually going to have to calculate the z-scores ourselves, which not as difficult as it sounds. In fact, as a hint, which I'm not going to do for you, But if you do a do file in which you just have this command, it's actually pretty easy once you get around to it. So we're actually going to assess whether the support for the difference between support black and support white are statistically different. So 0.5529 and 0.4900. So we're actually going to, first thing we're going to do is we're going to see what the difference between those are. So we're going to come back to our DR command. So 0.5529 minus we get this number right here. So this is what we're actually going to use in our test. Next, we're going to examine the square root of the standard deviations. And then we're going to square it. If you want to actually look at the equation, because I'm just trying to get the STATA commands to you today, if you want to actually look at the equation, go ahead and look at the book, because the book will explain why we're taking the square of something. The reason why we're doing it is to make it a non-negative number. But go ahead and look for the book for that. For the purpose of this video, I just want to get the STATA portion correct to you so you can see how it works. All right, so we've got, I think I did that wrong. Yes, I did. Hold on. No, I did that exactly right. Okay, good job, Todd. So we've got these two measures. Now we're going to take these two measures and we're going to plug them in to an equation which calculates the z-score. Now, about a z-score. A z-score is a transformation you make upon the data to assess it to assess for statistical significance. Now, it is not all that different from a t-score in terms of assessing statistical significance. In fact, as the population size grows, as z-score approaches asymptotics, it's actually a t-score. Or should I say, as the t-score approaches asymptotics, it's a z-score. So we use this primarily to examine sort of population parameters in data where it's, let's just say we use both. So we're going to actually plug this into the equation, which is, we're going to subtract it from the normal distribution, and then we're going to take and plug in our numbers. So 0.26608 divided by 0.0123667. And our z-score, not very high. So what it's telling us is that the statistical difference between the two does not exist. That's what you need to do your homework. The coefficient legend command is actually super useful, and it does solve the problems of the commands in the book not working. Note that because we're using STATA 16 here, the book was written with STATA 15. Not all the commands look the same. The output is almost exactly the same, but they don't all look the same, and some of them don't work exactly the same. So this is the workaround. Using coefficient legend, the lincom commands work perfectly, and everyone should still be able to do the homework as needed. Thanks.